Okay, so now what is the next meaningful question to ask is, okay, so this is how the train and the test are related, and now say fix, okay, let's say consider a fixed classifier, some h, right? So h is rd2 plus minus 1. Right. So, let us say there is a classifier, maybe my learning algorithm spits out this classifier, or I am just picking one classifier, which is just a function that maps the features to the labels, and I want to ask the question, how good is this classifier, right. So, I give you a classifier and I ask how good is this classifier. Now, I know that the test data is going to come from the same distribution that was used to generate the train data, right. So, which means that how should I mean the question of how should I measure the goodness of this classifier should depend somehow on the distribution that's generating the data, right. So, in other words, what is the, let's ask what is the error of h. How good is I mean you can measure goodness using error as well. The lesser the error, the better or more good the classifier is. So, how can we measure goodness of a classifier in terms of error? So, let us call this ER for error of h. Now, given a distribution D, if I told you what the distribution is, then can I put down what is the error of this classifier with respect to the distribution that's generating both the training and the test data? Well, what would that be? Well, one way to think of this is, if I generate, let's say, a test data point according to D, right? So, D is just this box with a button. I press the button, out comes x comma y according to some distribution D, right? Now, h of x would tell me h of x is telling me what h thinks should be the label for x, right. But now when I press this button, something came out, right. So, what came out is both x and y, and then I can ask whether what my classifier h says is same matches what the classifier, what the data point has, right. So, what the data point that came out of distribution D, right. So, in other words, I can ask whether h of x is not equals to y or not, right. And now I can ask what is the chance that this happens if I press a button to get x comma y distributed according to D, right. So, in other words, I can ask what is the probability of h of x not equals y if I randomly sample x comma y according to distribution. You can think of this as just the test error, right. So, this you can think of it as a test error. One way to think of this would be, what this probability, one way to imagine this probability is instead of sampling just one test data point, let us say I keep on sampling, test data points x test 1 comma y test 1, x test 2 comma y test 2, and I keep on doing this, and then I see what is the fraction of test data points that h misclassifies. And then if I do this experiment infinitely often, then that is going to look like the probability that h of x is not equals y, right. So, that's just law of large numbers, right. So you can think of you can think of what we are measuring as the test error, right. So, the chance that a randomly generated pair x comma y according to the same distribution that was used to generate the train data is misclassified by h is the error of h, is the test error of h, right. So, that's how we define the error of a given fixed classifier. So, now what is the goal, right. So, what should a learning algorithm do? If this is how we are going to measure error, then what should a learning algorithm do? Well, the learning algorithm's goal is just to first see which one, what can I talk about, how small can this error get, right. So that's what a learning algorithm should first ask, right. So now let's call that error D star, which is again a number between 0 and 1. Again, think of this because these are probabilities, right. So this is a number between 0 and 1. So what would error D star be? Well, over all possible classifiers, right. So minimum over all H, all possible ways of mapping inputs to outputs. If I look at error D of H, then that would be my error D star, right. So this is the smallest error any classifier can make. Now the question to all of you is, will this error be 0? Will this always be 0? The answer, I am going to tell you the answer now. The answer is this need not necessarily be 0. And we will see a simple example as to why this need not be 0. Let us say we are in a one-dimensional world, right. So we are just trying to understand what this error means, right. So let us say we are in a one-dimensional world, and my class 1, is centered at, let us say, -1, and then there is a Gaussian like this, and class, let us say class -1 is centered at -1, and then class 1 is centered at 1, right. So and then there is a Gaussian like this, let us say. For now, think of the variance as the same. Okay, so maybe this is slightly, looks like it has a higher variance. Okay, let me use a different color for the axis so that red and blue can be used for. Okay, so this is -1, and then there is +1, and this is another Gaussian. This is a one-dimensional variant of whatever we saw earlier, right. So this was a two-dimensional variance where you have these contours, but then here it is just a Gaussian. So what is this saying, right? So this is kind of saying that, and now let us say there is equal chance of seeing 1 or -1. Let us say P is 0.5 for the moment. Now if P is 0.5, now for any given x, right. So if I take an x, if I take some data point, because the features are one dimensional, if I take an x, now there is some chance that this x comes from P of y equals +1 given this x, right. So that is, the density is this much, it comes from the +1, right. So okay, let us say -1, y is -1 given x, right. So that is the red density. There is some chance that it comes from y equals, that the chance that y can be 1, right. So and these two need not be 0. What does this mean? This means that when I am actually generating the data, right. So for a given x, so let us say I generated the x first using some distribution, and now if I want to label y, so I want to toss a coin to decide whether x gets labeled 1 or -1. So all this is given by the underlying distribution d, right. So this comes from d, right. So let us say I factorize d as probability of x into probability of y given x, right. So d is just a joint distribution comma x comma y, right. So if I give an x comma y pair and I ask what is the chance that I see this in my train data or my test data, so that is what d tells me, the distribution tells me. Let us say it factorizes as p of x and p of y given x, and now for a given x, if it so happens that p of y given x is not just 1 or 0, that means that there is some chance that this x could have a label 1, and some chance that this x could have a label -1. If my distribution d is such that, then if I generate data from this, let us say I get a data point, let us say x in this case is -0.5, and I might get a data which is -0.5 labeled as, so this is feature, this is label, right. So for feature -0.5, this is -0.5, let us say. My label was -1, and then I press the button again, and this time what I got is -0.5, let us say I got -0.5 again, but then this time the label was +1, it could happen. This is a low probability event, right? So this is in this case a low probability event, but it's not a zero probability event, right? So there is some chance that this can also happen. Now, when this happens, what does that mean for H, which is the classifier that for which we are trying to figure out what its error is? The classifier is a deterministic function. Given a x, it's going to either say +1 or -1. It doesn't give you chances, right? So it just says this point belongs to class 1 or class -1, which means that the error then it need not be 0 even for the best possible classifier, right? So the best possible classifier has to take this, in this particular case, the entire one-dimensional data, and then it has to say, well, which are the points which go to class +1 and which are the points which go to class -1. Maybe in this particular case, the best possible classifier would kind of put a threshold somewhere here and say that everybody to the left is class -1, everybody to the right is class +1, right? So that's how the classifier is predicting. But then when we are measuring the error of that classifier, we want to ask the question, well, whenever the classifier is predicting +1, what is the chance that, you know, the label can actually be -1 according to D, right? So that chance is small, right? So if this is how the classifier predicts, that chance is small because +1 has a higher chance, but then it's not a 0 chance, right? So which means that I have to kind of integrate over the entire +1 region and then ask what is the chance that, you know, the label can be opposite of what the classifier predicts. And the same I have to do for -1 region and then add them up, and that would be my error of this classifier itself, right? So this need not be 0. That's the first point that I want to make here. The second point is the following. Now, what is the classifier? Which classifier makes error equal to RD star? Just a reminder, RD star is just the minimum over all classifiers RD of H. This is the test error. Think of this RD of H as the test error with respect to the distribution, and then I'm asking which is the classifier that has the smallest test error, right? So the test error itself is just the minimum over the value. It's just a value between 0 and 1, and we just argued it need not be 0, it can be some number. But I want to know which classifier achieves this. Well, it's not too hard to argue and prove this. I won't prove this, and this is achieved by what is called as a Bayes classifier, which is a very intuitive classifier if you think about it, right? So it just says the following, right? So let's call that H star, and now this classifier takes as input x, and then it either predicts +1 or -1. And when will it predict +1? Well, it will predict +1 if the chance that y equals +1 given x is greater than or equal to 0.5, and it predicts -1 if the chance that y equals -1 given x is less than 0.5. Sorry, y equal to +1 given x is less than 0.5, or y equals -1 is greater than or equal to 0.5. So this classifier is a super simple classifier and is the optimal classifier, and let's understand this a bit. So what is this classifier saying? This classifier is saying, you know, if you want to minimize the test error, then do the following. Given a x, check what is the chance that y is 1 for this x that you got. If that chance is 70%, it's greater than 50%, which means y equals -1's chance is just 30%. So 70% is greater than 30%, so you predict y as +1. Because remember, H has to make a deterministic decision, right? So it has to either commit to 1 or -1. The same is, you know, if the chance of y equals +1 is just 20%, well, it's less than 50%, so you will say y equals, H of x would say y is -1. So that's a very simple, super simple classifier. So in fact, we can prove that among all possible classifiers, if you fix a distribution D, then the classifier that achieves the least error in the way that we define the error, the probability of disagreement, is just the base classifier. Then one might ask, right? So one is then asking, why do we have so many algorithms if you know the optimal classifier? Why do we need SVMs? Why do we need logistic regressions? Why are we not using the base classifier, right? So that is the natural question to ask. Well, that's simply because of the way we are defining the base classifier itself, right? So the reason is the following: base classifier is a very intuitive classifier. The most reasonable thing you would do is optimal but cannot be obtained. And why is that? Here's a good time to pause and think, why can't I obtain base classifier? I'm going to tell you now, right? So, and the reason is because, it depends on D, the distribution that is used to generate the train data and the test data. And D is fixed but unknown. When I say fixed, it means that it's the same distribution from which IID all the training data and the test data is generated, but then it's unknown. Nobody tells us the distribution. The only information we know about D is via the training data, right? So training data, you have n samples from D, IID sampled from D, and that's the only information you have about D. You don't know anything more about D. If I knew D, if I know what D itself is, what is the actual distribution that's used to generate the training and the test data, then I don't need the training data at all. I can just throw away the train data. I mean, I don't care what the training data is because I know the distribution that's generating the train data, and I'm going to be measured only with respect to the distribution D, right? So that's what I really care about, error D of H, the test error. If I only need that, then I don't need the train data at all. If you give me D, then the train data is useless to me. I will just use D. I will compute for any given x what is P of y equals 1 given x, and if it is greater than 0.5, I will say plus 1, otherwise I will say minus 1. That's the base classifier. That's the one that makes the least error among all possible classifiers. The problem is we don't know D. And how can we get around this problem is, we somehow have to estimate D somehow using the samples that we have, right? So that you can make a statement about D itself. And that's the interesting question then, right? So because we don't know D, we cannot hope to get base classifier. So then what is our goal, right?